In this presentation, we'll learn how to apply an axial dispersion model to the salt displacement column that we have been running in the experiments in the laboratory. When we are looking at diffusion and convection of material through a cylindrical coordinates, and we have a plug flow type of liquid flow, we find that the change in concentration at any location with respect to time is equal to some axial effective diffusion coefficient and times the second derivative of the concentration with respect to the axial direction, d squared c dz squared, minus a velocity times the change in concentration with respect to z. In this particular model, t is time, c is concentration at a particular probe at time t, z is the distance of the probe to the inlet, u is the velocity of the liquid, and d effect is the dispersion coefficient. If the column is undergoing a step change in feed concentration, an analytical solution is available. The difference in the concentration at time t versus the initial concentration, c at t0, divided by the concentration when the time is allowed to approach infinity minus the initial concentration, will be equal to 1/2 times the quantity 1 minus the error function, ERF, of the parameters in the parentheses. Here's an example where we have 3 probes in a column, each 10 inches away from each other. Probe 1 is the closest to the inlet at 10 inches, and probe 3 is the furthest away from the inlet at 30 inches. In this example, our velocity u is 0.005 inches per second, and our effective diffusion coefficient is 0.01 square inches per second. And we can see the response at each individual probe as a function of time. By making our concentration dimensionless, it will start at 0 and end at a value of 1. This is the same situation, except now our effective diffusion coefficient is a value at 0.1 inches per second, inches squared per second. Notice that we start seeing a lot of backmixing in the column, and we do not have the concentration shooting up as we did in the previous slide. By increasing our diffusion coefficient to 1 square inches per second, now we see that we get much different results, and we're starting to approach a well-mixed system in terms of how our concentration responds as a function of the step input. Let's take a look at how we can apply this to our data that we gathered. I'm working from the data collected in run 11, where we have 2 probes, 2 and 4. 2 is located 20 inches from the inlet. Probe 4 is located 40 inches from the inlet. And when we first turned on the data logger system, we started when the liquid just reached the bottom of the marbles. And then we see the response as soon as the liquid reaches the probe location. For probe 2, it reached that location in about 11.9 minutes. And for probe 4, it reached that in approximately 24.8 minutes. We can use this to help calculate the velocity, since the distance between the 2 probes is 20 inches, and we can subtract the 2 times, and we'll find that the velocity in the marble section is about 1.55 inches per minute. Now there is 3 inches of tubing at the bottom of the column below the marbles, which also has a residence time. And we can calculate that knowing that the height of that is 3 inches. Now the velocity is not measured directly, but we can assume that the velocity is approximately half of that in the marble section, because spheres normally pack with a porosity of about 0.5. And so the time that the liquid travels through that bottom section would be the distance, 3 inches, divided by the velocity, which will be 1/2 times 1.55 inches per minute. And that will come out to be 3.88 minutes. When the salt was first turned on in this column, it was at 54 minutes. But we have to allow that additional 3.88 minutes for the liquid to travel through the bottom section. So we will call our time 0 at 54 plus that 3.88, or 57.88 minutes. And that will be the point where we start taking data so that we can fit it to our model. We also need to use the concentration at time equals 0. And in this particular case, we can look at just before we start transitioning to the change and average the readings over a period of time that we are confident we have a level value. And for probe 2, that concentration is about 521 microsiemens, and for probe 4, that is 520. We can get the value at time equal to infinity by looking at the concentration of the two probes for when they are at about a level value. For probe number 4, we find that the concentration at time equal to infinity is averaged out to be 13,468, whereas for probe number 2, that value is 12,636. Now we're going to look at applying the model. Here we're going to start our time 0 at 57.87 minutes. And that will be where we'll subtract that value from it and give ourselves a starting point for our step change. Our model can't accept a time equal to exactly 0, so I put in a value of 0.0001 and subtracted 57.87 minutes off of all the rest of the time. I then calculated using the formula for C star, using the experimental data where I used the conductance at that time minus the C0, divide that by the C at time equal to infinity minus C0, and I did that for each probe 2 and 4. I then also calculated C star by using the model, where we use the equation given below. And in this case, the only variable that I do not know is my effective diffusion coefficient. And so I assumed values and calculated that. So in this highlighted region, I used the value 0.256 for the first probe, or actually probe 2, and 0.360 for probe 4. These data were refined by using Solver to find the best value for the diffusion coefficient. Over on the right two columns, I calculated the square of the errors between the model and the probe readings, and then summed up all the square of the errors, and from where I switched on the salt until I just got ready to switch back to fresh water, and summed up the square of the errors for each column. I then used Solver to minimize the sum of the square of the errors by adjusting the value of the effective diffusion coefficient, which gave us a value of the 0.256 and 0.360. Here we see the experimental data along with the model fit for probe 4. I broke up the modeling in 2 steps. One is the region where we go from a fresh water to a salty water, and then we go from salty water back down to fresh water. So I used Solver twice, one to find the effective diffusion coefficient for the upside and one for the downside. The model is in the black line that you see represented in the slide, and experimental data is the blue line. So we needed to calculate 2 diffusion coefficients. One's going up and one's going down. So going up, we have an effective diffusion coefficient of 0.36 inches squared per minute, when we displace water with salt. And then coming down, that value turns out to be a factor of 100 higher when we take fresh water and try to displace salt. So our diffusion coefficient that best fit the data coming down is 35 square inches per minute where water is displacing salt. Now when you look at the data coming down and you actually plot C star, it will also start at 0 and end at 1. So what I did in that particular case is took 1 minus the C star calculated by the data and 1 minus the C star calculated by the model. And so it represents the data as it appears in the experimental section that we collected the data from.